Hello. In the previous lectures, we were discussing differentiability. In today's lecture, we are going to start with an important concept called as the um, Cauchy Riemann conditions. So far, I hope you might have done all the previous, you might have revised all the previous lectures. So uh, let us briefly discuss what we have done so far. Okay. So we had seen what does analytic function mean. And we had introduced the concept of differentiability. Having introduced the concept of differentiability, we had discussed analytic functions. Uh, a function is said to be analytic or simply holomorphic. I'm just writing it here. A function is said to be analytic or holomorphic at a point, let's say C. Let's say point A belongs to C. If it is differentiable not only at this point, but also in some neighborhood of A. Okay. So if it is differentiable, if it is differentiable at every point of some neighborhood of A. So uh, some neighborhood of A. So what I want to convey is that when I was talking about differentiability, okay, I was only concerned about a point. Let's say when I was saying that function is differentiable at A, it implies what? Limit h tends to 0, f of A plus h minus f of A divided by h must exist uniquely. Okay, so it must be a path independent limit. But uh, if I'm talking of analyticity, if I'm talking that a function is analytic at a point, then it must be differentiable in some neighborhood of A. That is, in this neighborhood, for all points, on all these points, function must be differentiable. I mean, there must be some neighborhood of A where your function is completely differentiable. Okay. And in fact, we have discussed that a function is analytic on a set S. So if I'm saying that function is analytic on a set S, then it must be differentiable. It implies it must be differentiable at every point. At every point of some open set containing this complete S, containing this set S. Okay. So initially, when we were talking of a point A, then it must be differentiable at that point. Then it must be differentiable at point A and also must be differentiable in some op open set containing A, that is some neighborhood of A. Now, if I'm saying it is analytic on S, set S, then it must be differentiable at every point of some open set containing S. So this is how you have to see the analyticity of a set S. Similarly, if I say that uh, for a closed disk, I have already mentioned that that closed disk must also be contained in some open set. Okay. So all these things we have done so far. Uh, Let us write a notation here first. So the set of all analytic functions set of all analytic functions in the open set D is denoted by simply this HD, because this H stands for holomorphic. Okay. So holomorphic is a synonym, or you can say another name for analyticity. So holomorphic I'm writing. Okay. So set of all analytic functions in the open set D is denoted by this particular notation. So I've introduced this notation now. And previously we've seen that if function is analytic on the complete finite plane, these functions are called as entire functions. We had also seen all the algebra related to that particular thing. So I'm not going to derive that. I'm not going to go into that. So without wasting time, let us start today's topic. That is the Cauchy Riemann conditions. Okay. So So we had seen previously that if even in the case of limits, continuity, uh, because complex analysis has a two-dimensional character, or you can say character of R square. So therefore, all the concepts that we have studied in multivariable calculus apply here. So in multivariable calculus also, if we have to uh, if we have to what? If we have to define differentiability, continuity, limits, all these things, we define that our limit must be path independent. Okay. So whether we find a limit in context of limits, whether we find the limit in context of continuity, or whether we find the limit in context of differentiability, our limit must be path independent, right? So this we have already seen. And one of the examples also we saw, I'm just revising it for you. Let's say fz is equal to z bar, and we want to find whether it is differentiable at 0 or not. Is it differentiable at 0? We have done this question previously, but just revising it for you before starting Cauchy. Is it differentiable at 0? So you would say, okay, let me find. So what is f of 0? F of 0 certainly is 0. F of 0 is certainly 0. What is going? Okay, so f of 0 is clearly 0. And now we have to find this kind of limit. Limit h tends to 0, f of 0 plus h minus f of 0 divided by h. And this would be simply equals to what? It would be simply equals to h bar divided by h. And now let us write our h bar to be equals to, let us say, h equals to, let us say, h1 plus iota h2. And if I'm writing that h tends to 0, it implies what? It implies h1 tends to 0 and h2 tends to 0. Okay. So what is h bar? H bar would be h1 minus iota h2 divided by h1 plus iota h2. And I know that if I take simply a path like this, that is h2 is equal to m times h1, then it will be like 1 minus iota m divided by 1 plus iota. So clearly this is a path dependent limit. This is clearly a path dependent limit. Okay. So clearly I would say that this function is not differentiable at z equal to 0. Okay, so all these things we have done. Similarly, we'll use this condition, that is whenever like use this condition of condition of differentiability, that the whenever we want to say that function is differential, we want to also express in the same line that our limit, that this particular limit should be path independent, and we'll use this and derive the celebrated Cauchy Riemann conditions. So let us define a function from D to C. So let us define the function from D to C. Okay. And let's say that fz is written as some u x comma y plus iota v x comma y. Here u and v are some real valued functions. Okay, here u and v are real valued functions. Okay, here u and v are real valued functions. Now, if f is differentiable, so let me just write it here. So if f is differentiable, then what does it imply? So let us say that h is equal to again h1 plus iota h2. Okay, so if f is differentiable, then this limit h tends to 0, u x plus h1, comma y plus h2 minus, sorry, plus iota v x plus h1 minus, sorry, comma y plus h2 minus u x comma y minus iota v x comma y upon, I'm so sorry, h1 plus iota h2. This limit must exist uniquely. Okay, and it should be path independent. If h tends to 0, it implies h1 tends to 0 and h2 tends to 0, right? Now, it is true uh, uh, for both h1 and h2 tending to 0. Now, what if I take a specific path, that is a specific path of approach, let us approach along the x-axis. Let us approach along the x-axis, that is, uh, let h2 be equals to 0 and h1 tends to 0. This also qualifies this kind of condition. Okay, so what will happen? This will be like limit simply h1 tends to 0. In fact, you can write this h1 simply, okay, I'll write it later on. So this is simply x plus h1 comma y plus iota v, and here you get what? X plus h1 comma y minus ux comma y minus iota vx comma y divided by simply h1. Okay, now you see, if you are really aware of your little bit about the definition for the partial derivatives, this condition qualifies what? Limit simply h1 tends to 0, and what it is equals to u x plus h1 comma y minus u x comma y divided by h1 plus, there's an iota here, v x plus h1 comma y minus Vx comma y divided by h1. Okay, so if function is differentiable, then this limit should exist. And what this limit is equal to? This limit is equal to what? This is equals to the partial derivative with respect of u with respect to x plus iota partial derivative of v with respect to x. So if function is differentiable, then this limit should exist and it should be equal to the derivative of function. So if function is differentiable, then f dash z is equal to what? Ux plus iota vx. This is first thing that we are getting. Similarly, if we take the path line of approach along this direction, that is, if we approach h tends to 0 in a way that h1 is equal to 0, but h2 tends to 0. Now, if we take this approach, what will we get? I'm directly writing, we'll get limit h tends to 0, u of x comma y plus h2 plus iota v x comma y plus h2 minus u x comma y minus iota v x comma y divided by simply h2. This we'll get if we take this line of approach, that is along the y-axis, that is h1 equal to 0 and h2 tends to 0. So if I take this line of approach, then what I'll get? Then I'll say that if my function is differentiable, then this limit should exist uniquely, and this is equals to what? This is equals to uy. Okay, use this and this. And this particular fellow is equal to what? This particular fellow, uh, okay, there was iota also, no? Sorry. So it is equals to, uh, uh, my bad, 1 upon iota. Okay, so this is equals to 1 upon iota. And then plus iota Vy divided by iota. Okay, so this iota will be remaining because h was equals to what? H was equal to h1 plus iota h2. Okay. So what I'll get? I'll get simply f dash z equals to minus iota uy plus vy. So f dash z is equal to what? Vy minus iota uy. So now, if my function is differentiable, then whatever path I would take, the limit should be path independent. It implies what? It implies that if the function is differentiable, then these two limits must be equal. And therefore, I would simply write ux should be equals to what? Vy and vx should be, sorry, I should write directly, or uy must be equal to what? Minus of vx. So these are called as your Cauchy Riemann conditions. That if function is differentiable, then this partial derivatives, that is ux, vy, and uy, vx, they must have this kind of consideration. That is, the partial derivative of u with respect to x must be equal to partial derivative of v with respect to y, and partial derivative of u with respect to y must be equal to what? Negative of vx. These are called as the Cauchy Riemann conditions. These are called as the Cauchy Riemann conditions. Okay. So this is very important thing that I have already mentioned. But we have to see a few things here. We should not make assertion that if Cauchy Riemann conditions are met, then function must be differentiable. If function is differentiable, then our u and v will satisfy the Cauchy Riemann conditions. This is absolutely true. But we cannot claim the converse right now. Okay. So we have to really make sure that this we are not over asserting right now. Okay. Another way of writing Cauchy Riemann condition. Okay, so there are a few more ways of writing Cauchy Riemann condition. I'll jot them down here. So this was the first way of writing Cauchy Riemann conditions. That is your partial derivative of u with respect to x must be equal to what? Partial derivative of v with respect to y. And certainly another condition is partial derivative of u with respect to y problem must be equal to partial derivative negative of partial derivative with respect of v with respect to x. So these are Cauchy Riemann conditions. Okay. Now further uh, I'm just giving you one example and letting you understand what I want to say. Okay. So what we have mentioned was that if f is differentiable, if f is differentiable, it implies what? It implies that Cauchy Riemann conditions must be met. Must be met. It implies what? It implies that if Cauchy Riemann conditions are violated at a point, then function is not differentiable at a point. Okay. So if either ux or uy and vx or vy do not exist, at a point, let's say z naught, then uh, function is not differentiable at z naught. In fact, another way of putting this can be if u and v do not satisfy Cauchy Riemann condition, do not satisfy Cauchy Riemann conditions, then also our function is not at, let's say, z naught, then function is non-differentiable. So these are necessary conditions, okay? But these are not sufficient conditions, okay? Now, it doesn't imply whatever I have stated, I cannot state the converse. So converse, not true. Converse, not true. That is, if Cauchy Riemann conditions are met, Cauchy Riemann conditions are met, it doesn't imply that at, let's say, point z naught, it doesn't imply that function is differentiable at z naught. So that is important thing one must remember, that if Cauchy Riemann conditions are met at z naught, then it doesn't imply that f is differentiable at z naught. So for this, I'm just taking an example. Let us say fz is equals to xy upon x square plus y square and if x square plus y square equal to 0, then this is simply equal to 0. Let us say this is our function, okay? Let us say this is our function. And let us first try to find the, what you can say, partial derivatives at 0. So that you will be able to get. So I'm just trying to make it easy by placing that. Let us think that our z naught is the origin point, that is z naught is simply 0. So let us first find what would be ux at 0, 0. So ux at 0 comma 0, if I think I'm just writing it for you right now. Otherwise, I think you must be well aware of this. F of h comma 0 minus f of 0 comma 0 upon h, and we know this will be equals to what? It will be equals to h into 0 divided by h square plus 0 square minus 0 divided by h, and this will be equals to 0 minus 0 divided by h. So clearly this is equals to 0. Similarly, you can one can find that uy at 0 comma 0 would be 0. Similarly, vx at 0 comma 0 would be 0, and similarly vy at 0 comma 0 would be equal to 0. So all these things I'm leaving up to you to really calculate. Definitions you know from your multivariate calculus course. So ux at 0 comma 0 is clearly equals to what? It is equals to vy at 0 comma 0, and uy at 0 comma 0 is clearly negative of vx at 0 comma 0. So both Cauchy Riemann conditions are met. Sorry, so Cauchy Riemann conditions are met. But is the function differentiable? But is the function differentiable at 0? Is the function fz differentiable at 0? You know that this particular function is not even continuous. This particular function is not even continuous at 0. If you want to really see this, you know from your earlier discussions that for function to be continuous, this limit must be equal to 0. However, when you find this limit, what you will get? Limit z tends to 0 means what? Limit xy tends to 0 comma 0, and what it is, you just take the path y is equal to mx, and I hope you're not getting confused. Fz means what? Basically, z is what? Z is simply x plus iota y. So clearly, it can be a function in both x and y. So don't get confused by this. So clearly, if I place the path y is equal to mx here, what I'll get? I'll simply get m x square divided by x square plus m square x square. So one would get what? One would get 1 m upon 1 plus m square, which is clearly path dependent. So function is not even continuous at 0. Leave differentiability. So if function is discontinuous at a point, then it is non-differentiable at that point. So clearly function is not even continuous at not even continuous at 0 comma 0. So leave differentiability, it's not even continuous at 0 comma 0. So clearly it serves as an example that the converse of Cauchy Riemann converse of the thing that we have derived, that is, if function is differentiable, then Cauchy Riemann conditions are true. But if Cauchy Riemann conditions hold, it doesn't imply that function is differentiable. So this is one of the examples which serves our purpose. Okay. Now let us do a few more things today, so that you will be able to get uh, you will be able to understand a new thing. Now, see, I'll come to this point later on, that what must be the sufficient condition. That we have already seen this thing, that if Cauchy Riemann conditions are met at z naught, it doesn't imply that f is differentiable at z naught. Now the question arises, what additional conditions must be supplied so that along with this Cauchy Riemann condition, so that function becomes differentiable. I'll write this particular thing as a statement later on. But now let us move to one more important thing. I'll come back to this particular point. Another form of writing CR equation. So complex form of CR equations. Okay, so for this, what we'll do, we introduce a notation. I'll do it another way also, but let us use another notation also. Okay. Uh, so we already have seen that if f is differentiable, if f is equal to what you wrote, I think we wrote u x comma y plus iota v x comma y. So if f is equal to this is differentiable at, let's say, point z naught, uh, then obviously we know that Cauchy Riemann conditions hold. Okay, then CR conditions hold. This we already know, and conditions hold. So I'm not going to write it. I'm just writing it. So Cauchy Riemann conditions hold. Now what we'll do, we'll write we'll use these conditions and see one important, what you can say, proof. Okay. So before that, I'll introduce a notation, introduce certain things. You already know that what is x. So if I'm saying that z is equal to what? Z is equal to x plus iota y, then what would be x? X would be equals to what? It will be equals to z plus z bar divided by 2. And what would be y? Y would be simply z minus z bar divided by 2 iota. This we know. Okay. Or simply if I had to write, I'll write simply minus iota, and I'll write z minus z bar divided by 2. Okay. So if your function f is differentiable at z naught, then CR condition hold. This you know. And I have written x simply as z plus z bar by 2, and y as simply minus iota z minus z bar upon 2. This is, I think, fine. Now let us introduce a notation. So I'm introducing I'll do it another way also, but just pay attention right now. I'll use another notation, and that notation is simply del by del z. This particular differential operator, I can write in what? I can write in this form also. That is simply sort of uh, this way. I hope this is clear. Okay. And obviously, z is function of z is has both x and y. So basically, I'll use this kind of thing. I hope this is clear. Okay. I know that what is del x by del z? I know del x by del z is simply 1 over 2. So I'll write simply 1 over 2 here. Okay. And what is del y? Interruption came. Okay. So what I was telling was, I I know that if f is equal to u plus iota v, and if it is differentiable at z naught, then Cauchy Riemann conditions hold. And I had introduced that x is equal to z plus z bar by 2 and y is equal to z minus z bar by 2 iota. And now I'm introducing the differential operators, that is del by del z. I know that z is equal to is equal to x plus iota y. So basically, uh, in writing this particular differential operator, I'm just using this kind of chain rule, that is del by del x into del x upon del z plus del by del y into del y upon del z. I know that del y upon del z is simply minus iota upon 2. So, so overall, if I write this differential operator del by del z, so this differential operator del by del z is equal to what? It is equals to 1 upon 2 del by del x minus iota del by. Okay, so this is one. And if I use this kind of thing, if I do not use this, if I use del by del z bar, what it will be equals to? It will be equals to 1 upon 2. Again, simply del by del x, this is fine. And here I will get plus iota del by del by. I think this is quite evident, so I'm not doing it for you. I hope you'll be able to do it. Now, having introduced both of these differential operators, uh, what would be fz? So it is simply del f by del z, and del f by del z would be equal to what? Del f by del z will be equals to 1 over 2. And here you will get del f upon del x minus iota del f upon del y. And if I use f z bar, differential derivative of f with respect to z bar, what I'll get? I'll simply get del f upon del z bar is equals to what? It is equal to 1 upon 2 del f upon del x plus iota del f upon del y. Okay, I hope it is clear. And okay, so I'm now going to write something that you know already. You know that f is equal to what? F is simply equals to u plus iota v. Okay, so I'll simply write 1 upon 2 outside. That is fine. And now just pay attention. Del f upon del x will be what? It will be equals to ux plus iota vx. So I'll be writing iota terms separately, and from here I'll get uy plus iota vy, and minus minus, so this will become plus. So you'll get simply vy here. I hope you'll be able to do all these things on your own. And with iota, what will be the term? I know that f is equal to u plus iota v, so I'll simply get vx, and from here I'll get simply minus of what? Uy. Okay, and this particular fellow I can write ux minus vy plus iota uy plus vx. Okay, so all you need to write here is, instead of f, just write u plus iota v. Now just pay attention. You know that f is differentiable, so it implies what? Cauchy Riemann conditions must hold. And if Cauchy Riemann conditions hold, then ux must be equal to what? Ux must be equal to what? Vy, and uy must be equal to what? Minus of vx. So it implies that if f is differentiable at point z naught, then it implies that Cauchy Riemann conditions must hold at z naught. It implies what? Cauchy Riemann conditions must hold at z naught. And if Cauchy Riemann conditions hold at z naught, it implies what? It implies that del f upon del z bar at z is equal to z naught must be equal to what? 0. So this is called as a complex form of the complex form of what you can say, complex form of Cauchy Riemann conditions. This is called as the complex form of Cauchy Riemann conditions. Okay, and this is an important thing. You should remember it. Okay, so so uh, we have already studied that a necessary condition for differentiability at a point is what? So a necessary condition is Cauchy Riemann conditions must hold. And in similar way, if Cauchy Riemann conditions hold, then it implies del f upon del z bar equal to 0. So I can also write that a necessary condition, a necessary condition for a complex valued function, a complex valued function f is equal to u plus iota v to be differentiable. to be differentiable at point z naught is that f z bar at z naught must be equal to 0, or simply del f upon del z bar at z naught must be equal to what? 0. Okay, so this is an important thing. So always remember that if now further, I know that if f is differentiable at a point z naught, then uh, Cauchy Riemann conditions must hold. And if Cauchy Riemann conditions are holding, it implies at that particular point z naught, del f upon del z bar must be equal to 0. If we are talking of analytic functions, that is, if I'm talking of analytic functions on domain D, I know that analytic functions means what? At if it is analytic at a point A, it implies it must be differentiable in the neighborhood, in some neighborhood containing A. So obviously, if f belongs to the set of analytic function, then CR condition must hold on this entire domain. So CR conditions hold at every point of every point of D, that is for all Z belongs to D. See, please understand this particular point. What I want to mention is that if f belongs to set of analytic functions, so let's say if a function is analytic on a domain D, then it implies that it must be analytic in some open set containing this domain D. So for every point in this domain D, function must be differentiable. And if function is differentiable on every point in this domain D, then clearly CR conditions must hold at every point of D. So this is very important. Okay. Now think about this. Think about this. What can you say about imaginary part of Z? Whether it is differentiable or not. So clearly imaginary part of Z is what? It is equals to Z plus Z bar upon 2. That is, if I'm writing my imaginary part of Z, Fz is equal to imaginary part of Z, then I can write Fz is equal to Z plus Z bar by 2. And if I want to now differentiate my F with respect to Z bar, I'm going to get 1 over 2. Clearly it is not equal to 0. So imaginary part of Z is nowhere differentiable. Okay. Since it is nowhere differentiable, so it is nowhere analytic as well. Similarly, real part of Z. So what is real part of Z? Real part of Z is simply, oh my bad. So this is, I think, real part of Z. And if I'm, sorry, no. If I'm writing real part of Z is Z plus Z bar upon 2. And if I'm writing imaginary part of Z, it is equal to what? It is equal to Z minus Z bar divided by 2 iota. So clearly I know that del f upon del Z bar is simply 1 upon 2 iota, or minus 1 upon 2 iota, which is simply equals to iota upon 2. So in any case, this is also not equal to 0. So imaginary part of Z is nowhere analytic, nowhere differential, therefore nowhere analytic, and real part of Z is also nowhere differentiable, therefore nowhere analytic. Okay. I hope it is clear till now. Okay. So even if you've not introduced this concept of if all these concept of what I'm saying, right? Operators, then also you could have done that. It's not that difficult. So let me just fastly do it so that you will be able to think that way also. I mean, this is very easy, but still I'm writing it for you. So we have derived complex form of Cauchy Riemann conditions, and I've already stated that my function fz is equal to what? It is equal to u plus iota v. It is differentiable. It implies the Cauchy Riemann conditions hold. That is ux is equal to vy, and uy is equal to what? Minus of vx. And if I write del f upon del z bar, so instead of now using the operator, I'll use the chain rule here. So del f upon del z bar is equal to what? It is equal to del u upon simply del x into del x upon del z bar. The same thing that we did there, I'm doing it here. Now plus del u upon del y into del y upon del z bar plus, now there would be iota here, iota del v upon del x upon del z bar plus iota del v upon del y, and here we'll get del y upon del z. So I hope it is clear. Okay. And I know that this is equal to what? This is equal to del u upon del x. And what is del x upon del z bar? Del x upon del z bar is simply half. So I will simply write half here. I think this is quite evident now. This, I think, already that x is equal to what? It is equal to z plus z bar upon 2. And what is y? Y is equal to z minus z bar upon 2. Okay. Okay. And what is del y upon del z bar? Del y upon del z bar is simply, I think, iota upon 2. So I'll simply write it as iota upon 2. Del y upon del z bar. No, iota upon 2 nahi. Del y upon del z bar is, I think this, I'll have to write minus 1 upon 2 iota. Okay. Plus iota. And what is this? Del v upon del x. So I'll write simply del v upon del x here. And del x upon del z bar is simply 1 over 2. And then plus iota. Del v upon del y will come as it is. And what is this? Del y upon del z bar. So del y upon del z bar is minus 1 upon 2. So this I will get del f upon del z bar. So it is equals to ux. So half, just take common out here. Just take half common out ux. And from here I'll get a real part. So iota cancels. So minus simply vy and plus this iota. If you just multiply below and above, so you'll get half here also. And here you'll get uy plus vx. Now, if f is if f is differentiable at a point, then these Cauchy Riemann conditions must hold, and so therefore this would be 0, and this would be also 0. So it implies what? It implies that del f upon del z bar precisely at that particular point would be 0. So obviously we are talking of differentiability at a point. Let's say at z0 I'm talking. So it implies that del f upon del z bar is 0 at that particular point. So whether you write it in sense of operator or you do it using the chain rule, they are giving you the same result. This you should remember, this is the complex form of the Cauchy Riemann condition. Now coming to the important conclusion that I told you. Achha, before that, let us do one more thing, that is the polar form of Cauchy Riemann condition. And then before ending up the lecture, I'll wind it up by writing the sufficient conditions. So polar form. The polar form of Cauchy Riemann conditions. Okay. Okay. We know that in polar form, x is given by what? R cos theta, and y is given by what? R sin theta. This we already know. Okay. So this I don't need to explain. Okay. This we already know. So now, and we know that what is the Cauchy Riemann conditions in Cartesian coordinate? Ux is equal to vy, and uy is equal to what? Minus of Vx. Okay, and I know that x is equal to r cos theta. So if I want to differentiate u with respect to r, what it will be equal to? It will be equals to del u upon del x into del x upon del r plus del u upon del y into del y upon del r. Okay, so this is what I'm going to get. And this is from the chain rule. Del u upon del x is fine. Del x upon del x upon del r will simply cos theta. So this I'm going to get ux cos theta, and then plus this is uy, and what is del y upon del r? It will be sin theta. So this is one. Okay. What about u theta? U theta will be same, del u upon del x into del x upon del theta. So you'll get ux. And what is del x upon del theta? It is minus r sin theta. And what is this? Plus del u upon del y. So it will remain uy here into del y upon del theta. So del y upon del theta is simply r cos theta. Okay. So u theta, I can simply write it as r times minus ux sin theta plus uy cos theta. Okay, so this is my equation number 2. And similarly, if I want to find what would be VR, so I'm directly writing VR would be what? Del V upon del X, this Vx into del X upon del R. So del X upon del R is what? Minus R cos theta. So I'll simply get minus R cos theta. Sorry, uh, del V. Sorry, I'll write it here. So VR is what? Del V upon del X into del X upon del R. Okay. So del X upon del R would be simply, I think, cos theta only. So that's not a worry. So Vx cos theta plus Vy sin theta, this is same. Third equation. And what would be V theta? V theta would be simply V minus Vx into R cos theta plus Vy into R cos theta. Okay, so this will be what? This will be your V theta. Okay. Now, we know from Cauchy Riemann condition that Ux is equal to Vy, and what you can say uy is equal to minus vx. So what we'll do, we'll write in place of ux vy, and in place of uy we'll write minus vx. Okay, now you'll do the same. So what is v theta? So v theta is simply what? V theta would be simply uh, instead of minus vx, I can simply write uy. So r taken common out, you will get uy cos theta, and plus instead of vy, I'll simply write ux. Uh, this is derivative now, so minus r sin theta. Sorry. So I'll get uy sin theta plus ux cos theta. Okay, so your v theta is what? V theta is simply what? V theta is simply r. And if you see what it is, ux cos theta plus uy sin theta. The ux cos theta plus uy sin theta was what? Uy. So v theta should be equal to what? R into ui. Okay. Now, if you think what would be your ur can be simply written as 1 upon r into v1 upon r into v theta. Similarly, if you want to find what is your u theta, so u theta is equal to what? U theta is simply, uh, I'll take r here and minus of ux. So instead of ux, I can write vy. So it is minus vy. That is that problem. I don't know. Okay, so u theta is equal to r. Instead of ux, I'm writing vy. So minus vy sin theta plus instead of uy, I'm writing vx. So minus vx, sorry. So minus vx cos theta. So what did I get? I simply got u theta is equal to minus r v by sin theta plus vx cos theta. And all of this is what? This is simply equals to VR only. So here u theta is equal to minus r VR. So both of these conditions are called as the polar form of the Cauchy Riemann conditions. So that is del u upon del r is equals to 1 upon r del v upon del theta, and del u upon del theta is equals to minus r del v upon del r. So this is called as the polar form of the Cauchy Riemann conditions. This is called as the polar form of the Cauchy Riemann conditions. Okay. Now coming back to the point which I was trying to make, we've already seen that if function is differentiable at a point z naught, then the Cauchy Riemann conditions must be met at point z naught. Okay. Now, and if Cauchy Riemann conditions hold, it doesn't imply that function must be differentiable at that point. Now, what would be the condition for sufficiency along with the Cauchy Riemann conditions at a point, so that function becomes differentiable precisely at that point? So what is that additional condition? I'm not deriving it, I'm directly writing it, that if f is defined from D to C, if f is defined from D to C, and your fz is equals to u plus iota v, and all the first order partial derivatives, that is ux, vx, uy, and vy, all the first order partial derivatives, that is ux, vx, uy, vy, exist at point, let's say z naught, that is x naught comma y naught, x naught comma y naught, and they are continuous as well. They are continuous at point x naught comma y naught. So not only existence plus Cauchy Riemann conditions are met, then it implies what? Then it implies that function is differentiable at point z naught, that is x naught comma y naught. So if your function, if Cauchy Riemann conditions hold at x naught comma y naught, it does not imply that function is differentiable at z naught. Additionally, these ux, vx, uy, vy, these all partial derivatives must be continuous at point x naught comma y naught. If this holds true, then this becomes the sufficient condition for the differentiability. Necessary condition for differentiability is that Cauchy Riemann conditions must hold. That is, if function is differentiable, then Cauchy Riemann conditions must hold at that particular point. But if Cauchy Riemann conditions are holding at a point, it does not necessarily imply that function is differentiable at that point. So therefore, we need to know what are those additional conditions by which I can imply differentiability. So if ux, vx, uy, vy exist and they are continuous at x naught comma y naught and Cauchy Riemann conditions are met, then function is differentiable at that particular point. So this is very important, and you should really remember that. Okay, so these all these conditions, I hope you're going to really remember. In the next lesson, that in the next lecture, we are going to qualitatively see all the more important points regards analyticity and the Cauchy Riemann conditions. Till then, take care. Bye.